In this video, I will talk about heteroscedasticity in R. Before you watch this video, please make sure that you have watched my other video called Heteroscedasticity. I have opened up the R script here and I have downloaded the data file called hprice1.csv. I have put it in this directory here. And I have run this program here, and these are the results in the console, which I have put instead of at the bottom to the side. What we're going to talk today about is, first of all, graphical analysis of heteroscedasticity. Then we're going to go over different heteroscedasticity tests, including the Breusch-Pagan white and alternative white tests. And we will finish up with weighted least squares and feasible generalized least squares. Okay, so first let's start with graphical analysis of heteroscedasticity. So we're going to read in a data set here called hprice1.csv. This is data that we have on house prices. And we would be calling this our data frame. So from our data frame, we will select several variables, including price, log price. So these are the price and log price for the house prices. This would be lot size of the house, square footage of the house, and then the number of bedrooms in the house. So for these variables, let's see the structure of the data, then summarize the data with Stargazer and see the first 10 observations. Okay, so we have 88 observations and 5 variables. These are the first few observations, and we are summarizing them here. These are the averages. So we have the house price in terms of thousands of dollars, the log of house price, the lot size, and then the square feet of the house itself, and then the average number of bedrooms is listed here. This is basically how the data looks like, the first 10 observations. So these are the values for each of the first 10 observations. So let's start with estimating a model for price. So here we would have price, that's the house price, regressed on these 3 independent variables, the lot size, the square footage of the house, and the number of bedrooms. And we would call this model 0. And what we really want from this is to get the residuals from model 0. We are going to call this U hat. So this is the residual from this model. And we would include those back in the data frame. And so next, let's plot these residuals. So first of all, here's how the regression looks like. So now we have, this is the house price, and then we have lot size, square footage, and the number of bedrooms. So this is how a normal regression output looks like. So because we're interested in figuring out heteroscedasticity, let's go ahead and plot these residuals. So we're going to do this in 2 different ways. The first one is we will be plotting the residuals against an independent variable. So for now, we're going to be using ggplot from this data frame hprice1. And what we're going to be mapping here is on the X line, we're going to have the square footage of the house, which is the independent variable. And on the Y axis, we're actually going to be plotting U hat. U hat was what we named the residuals from this regression. So we want to know how the residuals vary by an independent variable. And here we would be also plotting a y-intercept equals 0, so a horizontal line that would be red, and then we're labeling the vertical axis residuals and the horizontal axis square feet for the variable that we actually plotting here. So this is plotting the residuals against the independent variable. We can also plot the residuals against the fitted values. So here what we are going to be getting, so here instead of basically plotting the residuals against the square footage, we're going to be plotting this against the fitted values. So this fitted values is fitted from the model here that we have, model 0. So y hat are the fitted values. So here we're going to be plotting the fitted values against the residuals. Everything is the same. And for comparison purposes, these were regressions in terms of price. Now we will estimate a regression model in terms of log of price. So this linear model would be estimating log of price, and then we would put log of lot size and log of square feet plus the number of bedrooms. We're not going to be logging the number of bedrooms. But let's say this is another model that we want to be testing here for heteroscedasticity. And so from this model here, we would be picking up the residuals from model 1, and we will be calling this u hat 1. And so we would also be plotting the residuals u hat 1 from this model, both against one of the variables, which here is the log of square feet here, and we would be plotting this u hat 1 that is here against the fitted values. And so again, the fitted values from model 1 would be, we would call this y hat 1. So these are the fitted values from model 1. That's the model 1 that we have in logs. And so what we're effectively doing here is we estimated one model in terms of price on the original variables, and then we're estimating another model in terms of log of price on some of the variables being logged. And we want to be plotting residuals here. So let's go ahead and look at these residuals. So here are the residuals, these 4 residuals. So the first one is if we plot residuals against the independent variable, so the square foot against the residual. This is the graph that we see here. These are the residuals, so that's not the original data. These are not y, the dependent variable, which is price. That's not price. This is the residuals u hat. And here on the horizontal line, we just have x, one of the variables, independent variables. So now, in order for us to see homoscedasticity versus heteroscedasticity, if we have the case of homoscedasticity, then the variance of these residuals is going to be constant. It's not going to be changing. And if we have heteroscedasticity, the variance is going to be different. So this is very, very difficult to tell visually, but as we're looking here, we have much more variation here in the data and perhaps right here, and a little bit less variation here in the data. So perhaps this is telling us that there's a case of heteroscedasticity here. So now instead of plotting these residuals against the square feet, let's plot it against the fitted values. So now this is the fitted values, this is the y hat. And so again, we're seeing the same thing where we have here more variation in the data in terms of the residuals. And here we have a little bit less variation in the data. So again, maybe this is a case where we're going to have heteroscedasticity. Again, very, very difficult to tell by visual inspection. Okay, so now we have the model that we have a model for log price. So this is the log price on some of the logged independent variables, and these are the residuals from this regression. So we have y hat 1 and the log of square feet. So this is that one independent variable, and these are now the residuals from this regression. So notice that here, even though we have some spread here in terms of variance, overall we have a lot more tighter distribution that seems to be constant. So perhaps we have a case here of homoscedasticity. If we plot instead of this independent variable, if we actually plot the fitted values, we see the same thing, although we have an exception here and here with like higher variance here for these residuals. We still have like somewhat constant variance of these residuals here. So again, perhaps this is a case where we see a case of homoscedasticity. I would like to reemphasize how difficult it is to make a conclusion about homoscedasticity and heteroscedasticity just by visual inspection. That's why we need some formal tests to decide if there's homoscedasticity or heteroscedasticity. And these are the tests that we're going to be using here. So um, the heteroscedasticity tests involve estimating the regression model, regressing the squared residuals U hat squared on a combination of independent variables, and then doing an F-test or LM Lagrange multiplier test for joint coefficient significance. So this is what we're going to be doing next. Okay, so we would be starting with heteroscedasticity tests. Before we do that, though, let's go ahead and generate squares and interaction terms of independent variables, which we're going to need for some of the tests. So here we have the lot size, square footage, and number of bedrooms. Let's square these variables and call this lot size squares, footage squared, and bedroom squared. And then let's do the interaction of the variables lot size times square footage, lot size times number of bedrooms, and the square footage times bedroom. So we're going to be including these back in the data frame. So now the first model is to test for heteroscedasticity for price. So here we would have the same model as model 0. So just to remind you, that was the model of price regressed on lot size, square footage, and the number of bedrooms. And this will be the summary for this model. So again, we have here the coefficients of this model. So we're interested in, after we estimate the model, we're actually interested in getting the residuals U hat and the predicted values Y hat and then squaring them. So we already calculated these U hat, which is the residual coming from this model, and the predicted values, this is the fitted coming from this model. And so now what we need to do is just squaring the U hat to get to U hat squared and squaring the Y hat to get to Y hat squared. Okay, so now we're set up to do the Breusch-Pagan test. So this is the regression for the Breusch-Pagan test. So we're going to be running a linear model of U hat squared on lot size, square footage, and number of bedrooms. And let's go ahead and summarize uh, this regression output and just seeing the results here. So these are the coefficients here. So now notice that we don't have price here, uh, which was the original dependent variable. So it's not price regressed on the independent variables, but after we regressed price on all the independent variables, we got U hat, which is the residuals from that regression above. Then we squared them, and now this is the regression of the squared residuals on the independent variables. And these are the coefficients here. So now recall that what we really want in order for us to have a homoscedasticity is to have constant variance. So what that means in other terms is that this U hat squared should not have significant coefficients here to get homoscedasticity. If the coefficients here are significant, we would have heteroscedasticity. So I'm looking here at these coefficients and I'm seeing that one of them is actually significantly different from 0. So perhaps that's with the individual t-test. So now let's look in the f-test for heteroscedasticity. First of all, we're noticing that we have 3 independent variables. So this K1 would be the number of independent variables. So this is coming from this model BP. So that's that model BP. We're going to get the rank minus 1 would be basically the number of independent variables. That's why we get 3. We have 3 independent variables. So now the let's calculate the R squared. So here coming from the summary for this model, we're going to pick up the R squared statistic. And then we're going to get n-obs for n observation for the number of observations from the same model. And so we're getting 88 observations, and we're getting the r squared from this model is 0.16. Again, that's not the original model of price on the independent variables, but the u hat squared is this dependent variable on all the independent variables. That's the r squared that we want. Okay, so now the last thing to do here is form the F statistic using this formula here. So we could just plug in the r squared, the number of independent variables, and the number of observations, calculate the F statistic, and this is the p-value for this F statistic. And so the p-value shows that it's less than 0.05, therefore we have heteroscedasticity. Here the LM statistic is calculated by multiplying n times the r squared. So we're basically going to multiply n, which is 88, times this r squared, and that will be the number here 14 for the Lagrange multiplier statistic, and that p-value is also less than 0.05. So again, we have a case here that we have heteroscedasticity in terms of price when we test it using the Breusch-Pagan test. Okay, so instead of using the Breusch-Pagan test, we can also use two other tests. So basically, if the Breusch-Pagan test says that we have heteroscedasticity, we should go ahead and correct the standard errors for heteroscedasticity. But if it's not significant, perhaps we can also run the other tests here. So let's look now at the y-test, and then we're going to be looking at the alternative y-test. So for the y-test, how this is going to be estimated is we're going to be running a linear model of u hat squared, so that's the same as before. So up to here, we have the same as the Breusch-Pagan model. But for the y-test, what we're going to be adding is also the square terms and all of the interaction terms of the independent variables. So now instead of 3, we have 9 independent variables. So if we're summarizing the model that we have here for the y-test, these are the coefficients that we're going to be getting. And again, we want to have not significant coefficients. This would mean homoscedasticity. So here we only have one significantly different coefficient from 0. Okay, so the number of independent variables, of course, is 9 here. If you count the number of independent variables, that would be 9. And now we can calculate the F statistic and the LM statistic. And so here we're going to be picking up the R square. So from this model here, we're going to be picking up the R squared, and then the number of observations from this model here. And for the F statistic, again, we're going to be calculating it exactly the same way as above using this formula for the F statistic. And the p-value for the F test would be giving it the F statistic and the number of independent variables. This is degrees of freedom in the denominator, and lower tail test false because it's an upper one tail test. And same with the Lagrange multiplier. That's going to be multiplying n times the r squared. This is going to be the test statistic, and that is the p-value for it. So again, looking at these p-values here for both the f-test and the Lagrange multiplier test, we're concluding actually that these coefficients are jointly significantly different from 0. So while we're seeing that none of the coefficients is significantly different from 0 except for this one, actually they're jointly significantly different from 0. And so therefore, we are finding, again, a case of heteroscedasticity. The final model here is an alternative y-test where we are regressing y hat squared, not on the original variables like what we have here before, but we are regressing it on the y hat and the y hat squared. So these are the fitted values and the fitted values squared. And so the rest here is exactly the same, picking up the number of independent variables, which in this case would be 2, because we're going to have two independent variables, and then calculating the F statistic and the LM statistic. So just looking at these coefficients first on the alternative Y test, we're noticing that actually both of them are significantly different from 0 if we test them individually. Now, if we test them jointly, the F statistic using exactly the same formula as above is this, and this is the p-value. And for the LM statistic, when we multiply n times the r square, so we're multiplying 88 times this number here, 0.18 for the r square. So we have 16 for the test statistic, and this is basically the p-value for it. So once again, because the p-value is less than 0.05 here, we are concluding that these two coefficients here on y hat and y hat squared are jointly significantly different from 0. Um, okay, so once again, we're concluding that we have the case of heteroscedasticity here. Okay, so we tested price with 3 tests, including the Breusch-Pagan, the white, and the alternative white tests, and we found heteroscedasticity. So now let's very quickly repeat exactly the same tests, but this time for the log of price. So I'm going to go a little bit faster because everything is the same, except that the dependent variable and the independent variables, the dependent variable here is a little bit different. So here, I will use log price for the dependent variable, same independent variables. So let's see if we see heteroscedasticity in this model. So first of all, we're going to get the residuals and the predicted values and square them. So we're estimating this as linear model. We're calling this model 2. And from this model 2, we're going to pick up the residuals. We're going to call them U hat 1. We're going to pick up the fitted values or predicted values from model 2. We're going to call this y hat 1. And then we're going to square both the residuals and the fitted values. Okay, so now that we're set up, let's go ahead and run the 3 tests. The Breusch-Pagan tests is regressing the squared residuals on the independent variables. And then we're going to be using again the F test and the LM test for heteroscedasticity. So we need to know what the number of independent variables is, and then pick up the R squared and the number of observations to form the F statistic here. And then we'll calculate the p-value, and we can also formulate the LM statistic and then calculate the p-value for it. So if we look at these results here for log of price, if we regress log of price on the independent variables, these are the results here. So from this model here, we need to calculate the residuals and the fitted values. So basically, we need to calculate U hat right here for the residual and Y hat for the fitted value. And now the Breusch-Pagan test would be regressing the squared residuals on all of the independent variables. So looking at these, we don't, well, actually, only the coefficient on bedroom is significant at the 10% significance level, but it's not significant at the 5% significance level. So only this coefficient is significant. So let's do now a joint test here for significance. So using an F test, again, picking up the R squared, the number of observations. This is what we are going to be getting here. So this is the F statistic, that's the p-value. And for the LM statistic, multiplying n times R squared, this will be the LM statistic, and that's the p-value. So looking at the p-value, that's greater than 0.05. So basically, we have the coefficients are not jointly significantly different from 0. And we basically have that we have the case of homoscedasticity. Okay, so now let's do it a couple more times for the white test and the alternative white test. So the only difference from the Breusch-Pagan test to the white test is that if you look at the model here, that's the Breusch-Pagan test. If you look at the model here, the first part here is exactly the same as the Breusch-Pagan test for the white test, but then it's adding the squared terms and then the interaction terms. And so we repeat exactly the same thing. We find a number of independent variables, and then we get the F statistic and the LM statistic here. And we see that if we're looking at just the regression model here for the white test, we don't see any of the coefficients being significantly different individually. If we use the F test and the LM test, again, the p-values for them are greater than 0.05. So again, we are concluding that we have the case of homoscedasticity in the log of price. So for the last test, just to repeat things, for the alternative white test, again, we have now we're going to be regressing u hat squared on y hat and y hat squared. So basically, these are the fitted values from the model in logs. So again, this is the residuals from the model in log squared, and this is the fitted value from the model in log, fitted value squared from the model in log. And we're doing exactly the same calculations here to find that we actually, if you look at the F statistic and the p-value for it, and the LM statistic and the p-value for it, these p-values are greater than 0.05. So again, we have the results of homoscedasticity for the log of price. So these coefficients here are not significant individually, and then we also have these tests here showing that we have homoscedasticity for log of price. So the bottom line here is this. Using the three tests, Breusch-Pagan, white, and alternative white test, we find that the model for price has heteroscedasticity in it. The model for log of price is homoscedastic. So we can straight use the model with logs because it's satisfies the homoscedasticity assumption, and there's no problem just estimating as is. But in the model for price, because we have heteroscedasticity, we need to do some corrections. And how we do these corrections is with the so-called heteroscedasticity robust standard errors. So let's go ahead and actually implement these right now. So how do we do robust standard errors to correct for heteroscedasticity? First of all, let's recall that we have the model of price regressed on lot size, square feet, and the number of bedrooms. So this was the summary, and let's go ahead and look at the results again. So these are the coefficients and the standard errors using the original model, but now we established that we have heteroscedasticity. So kind of note that these are the values of the coefficients, and note that these two are significantly different from 0. So now if we want to calculate um, if you want to estimate a regression model for price with robust standard errors, how we're going to do this is we're going to use coefficient test, and then we're going to pick up these models 0 that we estimated here. This will be the variance covariance matrix that we're going to be using this. And here we are going to use for type HC1, which is heteroscedasticity consistent standard errors. So what we're going to see here is basically a correction for this model that we have here above. So notice that actually in terms of the coefficients, I know it's a bit different here scaling that we have in terms of using E, but these are exactly the same coefficients that we have before. So the coefficients don't change, but the standard errors change a little bit. So when we apply heteroscedastic consistent standard errors, and therefore, because standard errors are a little bit different, what we notice here is that this coefficient here on lot size actually lost significance, just barely lost significance. Here was significant, but here it lost significance after correcting for heteroscedasticity. So that doesn't always have to be the case, but in our case, that's what we see happen. So another thing is that we can also, in general, correct, estimate the model for log price, which we already done before. So this is the log price, and these are the independent variables. So this is our model 2 that we called model 2. And we can do exactly the same procedure here to find the heteroscedastic consistent standard errors. So these are these results that we have right here. This is the original model with the original coefficients, and these are the results that we have here. So notice that actually here we have some correction, and we do have uh, a little bit of loss in significance of this coefficient right here. But in general, we have much more similar standard errors here than before. And the reason for that is that robust standard errors are not needed since log of price is homoscedastic. We tested it above, we know it's homoscedastic, so we basically unnecessarily applied these robust standard errors, which doesn't hurt to apply them if they're not needed. But if you need to apply them, right, for example, like if price is heteroscedastic, then you absolutely need to apply the robust standard errors. So that's why many researchers always apply robust standard errors, because there's not much downside by applying them when they're not needed. But when they're needed, they really need to be used in the case of heteroscedasticity. Okay, so that's the easiest way to correct for heteroscedasticity, is just to use these robust standard errors. So basically this line here that we have. Now, there are a couple more approaches to correct for heteroscedasticity. So the first one is we're going to be using weighted least squares, and we're going to be using this weighted least squares when the form of heteroscedasticity is known. So here we would be assuming that the variance of u would be sigma squared times, let's say, square footage. So this will be one of the independent variables. So let's suppose that this is the known form of heteroscedasticity. Typically, it's very hard to know, but perhaps if you draw it against square footage, as we did in the beginning, you can see, say, for example, if the variance is increasing with this variable, then it may make sense to use this formula here if you visually see that this is what is happening. And so this is the let's assume that that's the correct form of heteroscedasticity. So now we can estimate weighted least squares with the weight equals to 1 divided by the square foot here. And so if we use this as the weight, that would basically bring the model back to homoscedastic model. So here's the first estimation procedure. So we're going to be estimating the model using weights of 1 divided by the square foot. And how we're going to do this is we're going to use a linear model. Here, formula would be equal to price regressed on these 3 independent variables from this data frame. And here, that's the new thing that we're going to be using here. It says weights equals to 1 divided by square footage. So here is how we do weighted least squares. We just put weight and what the weight is equal to. And that's going to give you the weighted least squares. So when we estimate this model, these are the results that we see here for the weighted least squares. Now, when we were doing the heteroscedasticity robust standard errors before in the procedure before, one thing that we noticed is that the coefficients were the same, only the standard errors changed. But here we would actually see that the coefficients are also a little bit different than the coefficients that we had on the original model, and also the standard errors are a little bit different in this case. So, and the reason for that is that the weighted least squares uses these weights that would also affect the coefficients here as well. So these are the new results after we correct for heteroscedasticity using the weighted least squares. So different coefficients, different standard errors than we had before, but overall similar conclusions here. So both of these coefficients were actually significant before, and they're still significant now after correcting for heteroscedasticity. Now, what this line of code is doing here, we could do it slowly, and the way that we can do it slowly is we can divide each of the variables here, price, lot size, square footage, bedroom, including the constant in the model. We would be dividing this not by square footage, by the square root of the square footage. And so here, notice how the weight is 1 divided by the square root, but the transformation is here. We got to multiply this times 1 divided by the square root of the square footage. So this will be this multiplication factor that we see here. And now we could do the weighted least squares on the transformed model. So here we would have, instead of price, we would have this price star, where this is the transform variable. It's not going to have an explicit constant because this is now the transform constant that we have here. And all of these starred variables are going to be right here included in the model. So this transformation that we have here is equivalent to using the weights. That's what we've seen in the lecture. And if you notice these coefficients here and the standard errors, everything is identical between the two different ways to actually calculate these weighted least squares. So this is why it makes sense to just use the linear model here with the weights as you estimate WLS, rather than transforming manually each of the independent variables. So finally, let's talk about feasible generalized least squares, and this is when the heteroscedasticity form is not known. So in this case, we would assume that the variance of u is sigma squared times, and this would be an expression that depends on the independent variables, and because we don't know these coefficients, we would be estimating basically this functional form here. So the goal here is to estimate this h hat and use it in weighted least squares with the weight of one divided by h hat. So in order to do that, let's first estimate the original model of price on the independent variables. And then from this model, then let's pick up the residuals from this model 0. And then we would call these u. So let's calculate the squared residuals. Take the log of them, that will be the g function. So now we're going to estimate the linear model of g regressed on all the independent variables here. And from here, once we estimate these coefficients, we're going to be picking up the fitted values from this model. We're going to call this g hat, and we're going to exponentiate this g hat to get back to h hat. So this is basically how we do the transformation of actually estimating this heteroscedasticity form here when it is not known. So now that we have this h hat estimated, what we're going to use it is in the model that we have here, we're going to use this as the weights. So 1 divided by h hat would be the weights that we have here. And so this is the feasible generalized least squares, where we're going to have price regressed on all the independent variables with weights of 1 divided by h hat. So now we can also estimate the same model in an alternative way, which is by dividing each of the variables, including the dependent variable, the 3 independent variables, and the constant, by the square root of this h hat. So notice always that the weight is 1 divided by h hat, but we're multiplying this by 1 divided by the square root of this h hat. Uh, so now we can estimate a regression model using these transform variables that have stars on them. And so here we would have the price star regressed on, we're not going to have a constant because we transform this constant here for the model, and then each of the independent variables are going to be transformed. So if we were to look at the results, this was the original model that we had here, where we have the price regressed on the 3 independent variables. So we were needing this to estimate the form, the heteroscedasticity form, which was unknown. And then using this h hat, we can estimate the model. So now notice that basically we get exactly the same coefficients here, whether we are using this approach here of using weights of 1 divided by h hat, or this approach here where we are rescaling all the variables by multiplying them times 1 divided by the square root of h hat. So these coefficients here are the same to each other. Now, if you compare these generalized uh, feasible generalized least squares coefficients and standard errors to the original ones or to the WLS, you're going to see that these coefficients are a little bit different because we have different weights. So here both the coefficients and the standard errors are a little bit different. But if you actually compare the significance level, that is very similar to what we had before, both with the OLS and WLS. And again, this is specifically in our case, it doesn't always have to be the same. So we have similar results. So again, what we've done in this program here, we have tested for heteroscedasticity by visually inspecting it, then using the 3 tests, Breusch-Pagan, white and alternative white tests. And if we find heteroscedasticity, we need to correct them with robust standard errors, or we need to estimate WLS or feasible generalized least squares. So this concludes the presentation on heteroscedasticity.